Dear student, I am Dr. Harold Thomas, Professor in Applied Geology, Dr. Hari Singh Gaur Vishwavidyalaya Sagar. Today, I will deliver my lecture on Metamorphic Facies series. Hope it will be useful for you. Try to be regular in course. The change in mineral assemblages are due to change in the temperature and pressure condition of metamorphism. Thus, the mineral assemblages that are observed must be an indication of the metamorphic temperature and pressure environment that the rock was subjected during metamorphism. This pressure and temperature environment is referred to as metamorphic phases. It was believed that the Barrovian pattern of metamorphic zones represent the normal type of regional metamorphism. Intensive study of regional metamorphism in Japan and also other parts of the world since 1960 has shown that the respective pattern of zoning differ from the normal Barrovian type. This led Mayasiro in 1961 to propose the concept of Facies series. This can be represented by a curve or a graph of curve in a pressure temperature diagram. Therefore, each Facies series involves a definite regional distribution of temperature and pressure, or in other words, a definite geothermal gradient expressed in degrees Celsius per kilometer. Thus, in case of higher geothermal gradient, a particular temperature realized at a low pressure, whereas in case of lower gradient, the same temperature operates under higher pressure. The Barrovian sequence chlorite, biotite, garnet, sterlite, kyanite, sillimanite, that is greenschist, epidote amphibolite, amphibolite and gammolite facies, is on such Facies series. According to the location of the curve or curves, the Facies series may be classified into various types. Mayasiro in 1961 recognized 5 types of Facies series. First, low pressure or Andalusite sillimanite type, and Abukama type of greenschist, amphibolite, gammolite characterized by the paragenesis of Andalusite and sillimanite type. This is similar to Buchan type of Dalendian, corresponding to a geothermal curve running on the lower pressure side of the triple point of Al2SiO5 polymorphs. Geothermal gradient is less than 25 degrees centigrade per kilometer. Second, medium pressure or kyanite sillimanite type, typical Barrovian sequence of greenschist, epidote amphibolite, amphibolite, gammolite, characterized by sillimanite, kyanite type. Geothermal curves running on the higher pressure side of the triple point of aluminosilicates polymorphs. Geothermal gradient is 20 degrees centigrade per kilometer. Third, high pressure or jadeite glaucophyne type, a geolite, prehenite, pumpelite, blueschist, eclogite type, in which geothermal curve approaches or cross the higher pressure stability limit of jadeite quartz. Pressure temperature gradient is 10 degrees centigrade per kilometer. Fourth, low pressure intermediate type. In this case, the pressure temperature gradient is between 1 and 2 Facies series and passes through the vicinity of Al2SiO5 triple point. This all the 3 polymorphs, normally Andalusite, sillimanite, kyanite, occurs in peltic rocks in this Facies series. Fifth, high pressure intermediate type. In this case, the pressure and temperature gradient between 2 and 3, this is similar to kyanite sillimanite type, but with glaucophyne 2, never jadeite plus quartz in the same assemblages. Mayasiro recognized that these different Facies series represent different pressure temperature conditions and trained as in figure. He called them baric types. First, high pressure or glaucophene jadeite blue cyst eclogite type. Second, intermediate pressure temperature or kyanite sillimanite type. And third, low pressure temperature or andalusite sillimanite type. The change in mineral assemblages are due to changes in the temperature and pressure condition of metamorphism. Thus, the mineral assemblages that are observed must be an indication of the temperature and pressure environment that the rock was subjected. This pressure and temperature environment is referred to as metamorphic phases. After the discovery of plate tectonic in the 1960s, a new framework was opened to study the metamorphism. Mayasiro in 1961 had correctly recognized that the observed metamorphic Facies series is a function of tectonic environment. He observed that different Facies series are encountered in different orogenic belts and in different setting within orogenic belts even before the advent of plate tectonic provided a framework for interpretation. After the discovery of plate tectonic, it becomes clear that glaucophene jadeite metamorphism is associated with subduction zone metamorphism. Ernest, who recognized the study of high pressure temperature metamorphism, could suggest information about the dynamics of subduction zone and evolution of plate tectonic over time. Figure 1 and 2 created by Ernest in 1973 to show the relation between metamorphic Facies types and plate tectonic. In figure 1, a divergent plate is shown. Isotherms shown in figure are blown up at ridges because this is the locus of upwelling mantle and intrusion of mid-oceanic basalt. With increasing depth at ridge, one can observe the low pressure Facies series with geolite Facies to green cyst and after amphibolite and gaolite low pressure varieties near the magma chambers, because new crust continues being created due to intrusion of magma. The metamorphic Facies shown in figure 1 will migrate laterally with time. Hence, it is possible that the entire oceanic crust is metamorphosed to the amphibolite to gaolite Facies at the base. In order to convert unmetamorphosed oceanic crust into metamorphic green cyst and amphibolites, water must be added to the rock. In the absence of added water, no metamorphism will take place. Therefore, it is not necessary that entire oceanic crust is metamorphosed simply because the temperature are metamorphic temperatures and the metamorphism may be restricted to places where water has access. In figure 2 is shown a convergent plate margin. The isotherm in figure are blown downward into the subduction zone because the subduction processes carries cool lithosphere downward into the mantle in the vicinity of the island's arc. The isotherms are blown up because hot rising magma carry heat from the mantle upward and low pressure temperature andalusite sillimanite type. The sequence of Facies encounter going down the subduction zone is geolite, prehenite pumpelite, blue cyst and eclogite. In contrast, the sequence of Facies in the Iceland arc is geolite, prehenite pumpelite, green cyst, amphibolite, gaolite. Paired metamorphic belt. On the basis of figure 2, it revealed that there is a polarity to the metamorphic Facies in the subduction zone. that is, the increase in metamorphic grade from zeolite, prehenite pumpelite, blue schist to eclogite take place along the dip of the subduction zone, because this is where the isotherms are blown down. Ernest in 1971 observed that this polarity is the key to determining the dip of ancient subduction zones. Recognized that unless the subduction complex become completely inverted, then the dip of the ancient subduction zone should be in direction of increasing metamorphic grade. Figure 3 shows selected data compiled by Ernest in 1975 for Japan. In Japan, the metamorphic grade increases from zeolite facies through blue schist facies with some green schist and amphibolite overprinting as one traverses to the northwest. The juxtaposition of high pressure temperature and low pressure temperature metamorphic facies type has been called Mayashiro, a paired metamorphic belt. The low pressure temperature metamorphic belt is the ancient Iceland arc, which is this case has been thrust up against the subduction complex. Dear student, today in this lecture we have discussed about the metamorphic facies series and plate tectonic. I believe this lecture was useful for you. For further studies, please read the textbooks, references and links given in the text. Thank you very much.